I have posted the slides for each chapter onto Canvas. So open up the slides for chapter 11. That's where we're going to start. Okay. Now on slide 1, you will notice that we have properties of solutions. Okay, and that's going to correspond to chapter 11. Okay, also on that slide, we are going to have the book problems that you need to complete for that chapter. All right, now moving on to slide 2. Okay, the first topic, now most of this stuff from chapter 11 is going to be review from 121, right? It's going to be that last bit that you guys covered in 121. Okay, now, first thing I want to talk about is molarity. All right, now, molarity is defined as capital M, which is the moles or N of solute over liters of solution. Okay, so again, that's moles of solute over liters of solution. Okay, now here, our solute, that is the thing or the substance that is being dissolved. Okay, and your solvent is the substance that is dissolving the other substance or is dissolving the solute. Okay, so for example, if I added, like say I was making sweet tea and I added the sugar into water, right? The substance that's being dissolved, the sugar, would be my solute, okay? And the solvent in that case, the thing that's dissolving the sugar, is going to be the water, okay? So let's say that we have, let's say we do this example, let's say that we have 1.00 moles of sugar and 125.0 liters of solution. Spell solution. Okay, then let's calculate our molarity. All right, now our molarity is defined as our moles of solute, our N of solute, over our liters of solution. Okay, so what is that going to be equal to? Well, we have 1 mole of sugar, 1.00 moles of sugar, right? Because sugar was our solute, that's what's being dissolved. Our solvent is this other solution, right? But we have our total volume of solution. Okay, notice it doesn't say liters of solvent, it says liters of solution. The solution is going to contain everything, so it's going to have our solvent and our solute together as the solution. Okay, so notice it gave me my volume in liters of solution, which was 125.0 liters. So dividing through, this is equal to, oh, sorry, this was supposed to be 125 milliliters. All right, so that would make this not 125 liters, but 0.125 liters, 1250, right, to keep all of our sig figs. So dividing by that, we get 8.00, right? Because we have 3 sig figs on the top, so we're going to have 3 sig figs over here. And that is going to be 8.00 molar, okay? Molar. All right? So that would mean that we have an 8.00 molar solution of sugar, okay? Now, the next thing that I want to talk about is on slide 3. Okay, now slide 3, we talk about our mole fraction. Okay, now the mole fraction is going to range from 0 to 1. Okay, because it's going to be a fraction, right? So our values can be from 0 to 1, just like normal fractions. Okay, but our mole fraction if we are talking about a liquid solution, so mole fraction in a liquid, okay, we denote that as X sub A, where A is the substance, mole fraction, so this would be our mole fraction of A in liquid, which would be XA, which is defined as our moles of A, so N of A, right, over our moles total in the solution, okay? So again, that's moles of whatever we're looking at, A, over our total number of moles, all right? That's important, okay? And I should probably box around this one as well. Make sure that you write down these equations because they're going to be important, all right? Now, let's say that we have a solution of H3PO4, right? That's phosphoric acid. Solution of phosphoric acid that was made by dissolving 8.00 grams of acid in 100 milliliters of water. All right, well, what's the very first thing that we're going to do? We need to figure out what our solute is and what our solvent is, right? So in that case, our phosphoric acid is what's being dissolved into the water. So our phosphoric acid would be our solute, and our water would be our solvent, okay? So we put this in here, right? Now, let's calculate the mole fraction, okay? Now, since we are talking about H3PO4, right? So I had mole fraction of A. If I want the mole fraction of H3PO4, right? I want to calculate that. All right. What am I going to do? Well, first thing we need to assume is that water has a density, rho. So our density of water, sometimes people put D, okay? I use a little rho, it kind of looks like P, has a density of water that's equal to 1.00 grams per milliliter, okay, at that particular temperature, okay? Now, we know that we want to find our mole fraction of H3PO4, which is going to be equal to our moles of H3PO4 over our moles total, okay? So we need to first figure out our moles of H3PO4, okay? Well, how are we going to figure out our moles of H3PO4? We have the grams, so let's use our molecular weight, all right? So we have 8.00 grams of H3PO4, all right? And then 1 mole of H3PO4 corresponds to 97.994 grams of H3PO4. which is going to be equal to 0.08164 moles of H3PO4. Okay, that's what we needed for the top. Okay, so the next thing that we need to figure out is our moles total. All right, well, in order to do that, we need to figure out how many moles of water we have in addition to our moles of the acid. All right, so let's say that we have 100 milliliters, right? We have 100 milliliters of water. Okay, so let's take our 100.0 milliliters. All right, water at this temperature is 1 gram per milliliter. Okay, which means that we have 100 grams of water. Okay, so now we have the grams, so let's convert that into moles. We have 100 grams of water and 1 mole of water goes over 18.016 grams of water, again using my molecular weight. Now, the thing to keep in mind with molecular weight is, all right, since we're starting with grams and we want the grams to cancel, we're going to put our grams on the bottom and the 1 mole on the top, okay? If we were going from moles to grams, right, like say I had 10 moles and I wanted to convert that into grams, right, it would be, we put our 1 mole on the bottom and we'd have our 18 grams on the top, okay? But again, that's not what we're doing right now. We're converting grams into moles, so our grams are going to go on the bottom for our molecular weight. All right, so that is equal to 5.5506 moles. Okay, so now I have this many moles of water, and I have that many moles of the phosphoric acid. So in order to calculate my mole fraction, all right, my mole fraction of H3PO4, that's going to be equal to my moles of H3PO4. My moles of H3PO4 were 0.08164 moles. And what are going to be my total moles? It's going to be this plus that. All right, everything that's there is added on the bottom in moles. All right, so I'm going to have 0.08164 moles plus 5.5506 moles, which is equal to 0.0145. All right? So that's how we calculate our mole fraction. Again, it is moles of the species that we're interested in over our moles total. All right, now moving on to slide 4. Here we're going to calculate our mass or volume percent, right? So we could do it either one, right? We could either use mass or volume. All right, so if we're calculating our mass percent, all right, sometimes it's called the weight percent. All right, so if we're calculating our mass percent, that's m sub percent, that is going to be equal to the mass of the solute over our mass of solution. Okay? Then we're going to multiply by 100 to get it in terms of percent. All right? So, what is the percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water. All right, well, if we take a look at our mass percent formula, right, we need our mass of our solute divided by our mass of the solution. All right, now remember that the mass of the solution contained everything, right? So, right, because if we were talking about the solute would be 5.5 grams. Okay, so we have our mass percent is equal to our mass of solute. Our solute was 5.5 grams of glucose, okay, because that was our solute. All right, and then on the bottom it needed to be the mass of the solution. So this was the solute, this was our solvent, okay, because the water's doing the dissolving, okay. So our solution has to be both of those added together. So we have 5.5 grams plus the 78.2 grams, okay, and that would be our mass total. Then we're going to multiply by 100 to put it into percent, which will give us 66% glucose all right, and then we say by mass, okay? Since we use the masses here, it's the percent by mass. If we used volumes, okay, which would be the volume of the solute divided by the volume of solution, okay? If we did the volume percent, then it would be percent by volume, okay? But since we use the masses, it's the percent by mass, or the mass percent. All right? Now, moving on to slide 5. Now we're going to talk about molality. Earlier we talked about molarity. Now we're going to talk about molality, okay, with an L, okay? This is denoted with a little m, okay, a little curly kind of m, right? So we have that the molality is equal to the moles of solute, okay, over kilograms of solvent. Okay, so we have our moles of solute over the kilograms of solvent. Okay, notice that this is the solvent, not the solution. Not solution. Okay, so remember here, because we had to do it in terms of the mass of the solution, we had both of them on the bottom. Okay, in this case, for molality with the little L, it's the solvent. Okay, so it would just be the water. All right, so let's say that we had a solution of H3PO4. We're making that same phosphoric acid solution from before. Okay, made with 8.0 grams of the H3PO4 and 100 milliliters of water. Okay, now what's the molality? Okay, well, our molality, as we said, was defined as the moles of solute divided by the kilograms of solvent. Okay, so let's first get our moles of solute. All right, well, the N of the solute, right, that's going to be equal to 8.00 grams, right, because we're going to convert the grams into moles. So let's just start with that, right? So we have 8.00 grams of H3PO4. All right, and then we're going to use the molecular weight, okay? Now, the molecular weight for phosphoric acid was 97.994 grams per mole. So that means that since we want to cancel the grams are going to go on the bottom, and we have the 97.994 grams, right? Because we want the grams to cancel. And then the 1 mole, because it's always per mole, all right? The 1 mole of the phosphoric acid goes on top, which is going to give us 0.08164 moles of the phosphoric acid. All right, then we need the kilograms of solvent. All right, well, we have 100 milliliters of water. All right, and we know from earlier that our density for water is 1 gram per milliliter. All right, so we have 1 gram on the top and we have 1 milliliter on the bottom. All right, so we have 100 grams of water. All right, now I need it to be in kilograms. Okay, so for kilograms, right, we know that there are 1,000 grams per 1 kilogram. Again, we're going to put our grams on the bottom to cancel with the grams. So that would mean that we have 0.100 kilograms. Okay, so that means that we are now ready to evaluate into our molality expression. Okay, now again, our molality, little m, that's equal to our moles of solute over our kilograms of solvent. Our moles of solute was 0.08164 moles all over my 0.100 kilograms, which was equal to 0.8164 molal. So remember when we had the big M for molarity, this was an R. Now with the little m for molality, this is molal. Okay? So that is how we get molality. The next thing that I want to talk about is called normality. Okay? Now, normality, and this is going to be on slide 6, okay? Normality can be a little bit tricky, okay? Now, basically, it's going to be the concentration of an active species. Okay, so for example, right, e.g., that would be protons for an acid, hydroxides for a base, etc. Okay, and I'll sort of show you what that means, right? So let's say that we have citric acid. Okay, so we have 1.37 molar citric acid, which is 8,3C6H5O7. Okay, so H3C6H5O7. Okay. Now, the citric acid has 3 acidic protons. Okay, now since it has 3 acidic protons, then that means that it's going to have a concentration of H plus, okay, that is 3 times 1.37, which is equal to 1.37 molar, which is equal to 4.11 normal, okay, with a big N. All right, so another example would be, let's say we have 2.0 molar calcium hydroxide. Okay, that's calcium, and then we have OH, and then we have two hydroxides, right, that are bound to the calcium. Okay, now, as I said, the active species are going to be the hydroxides for the base. Okay, well, how many hydroxides do we have? We have two hydroxides. Okay, so that means that we're going to take 2 times our concentration of this species, which was 2.0 molar, and that will give us 4.0 normal. Okay, basically it's the concentration of that active species. Okay, just the OH. All right, now as another example, let's say that we have 6.0 molar HCl. All right, that's hydrochloric acid. Since it's an acid, we're going to be looking at the protons. That's right. So, how many protons do we have? Well, we have 1 proton, right? We have 1 H plus. Okay, so I'm going to take 1, multiply that by my molarity to get 6.0 normal. Okay, again, that's sort of like the concentration of the active species. Okay, now if we had 6.0 molar phosphoric acid, right, that's H3PO4, well, how many acidic protons does it have? It has 3. Okay, so that means that we have 3 H pluses that can be used, which means we will have 3 times 6.0 molar to get 18.0 normal. All right, now there are a couple of example slides, slides 7 and 8. I recommend that you give those a try before we start the next video. All right, but I will be walking you through how to do those in our next video.